Okay, so we've seen how quaternions can describe points in orientation space. In particular, a quaternion corresponds to a rotation. A unit quaternion corresponds to a rotation. And we know that rotations are in one-to-one correspondence with orientations. So in this way, we can think of quaternions as describing spatial orientations, points in orientation space. Now let's see how they can parameterize paths in orientation space. So to begin with, let's start with a simple non-trivial loop, namely the 360-degree rotation loop about the x-axis. So here's Bala, here's my x-axis, and my 360, he's going to be rotating in this direction. My 360-degree rotation loop, it's a movement sequence. It begins at this base orientation. He starts rotating, 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 and he's back to the base. That's my 360-degree rotation loop. So how do we parameterize this using quaternions? Well, we can write a simple formula. So this path is parameterized by p of theta equals cosine of theta over 2 plus sine of theta over 2i. So as theta ranges from 0 to 2 pi. So when theta is 0, we're here. When theta is, say, pi over 2, we're here. When theta is pi, we're here. Now theta is equal to 3 pi over 2. Now theta is equal to 2 pi. So as theta ranges from 0 to pi, we perform this full rotation loop. And the reason it works just comes from the bijection we looked at earlier. The axis throughout, for every quaternion p of theta, the axis is always given by 1, 0, 0. It's always the x-axis. All that's changing is the angle, and that angle is slowly increasing from 0 to 2 pi. So this gives us the 360-degree rotation loop about the x-axis. So the nice thing about writing this out in this precise formula is that we can plug it in to a computer. For example, you can use if you're familiar with Blender, doesn't matter if you're not, it's a 3D animation software. It's fully open source. You can download it right now and start using it. And actually the things that we're doing on it, that I'm in this class, are relatively low intensity. So even on a computer that's not very powerful, you should be able to manage some of these rotations of spheres. So so I just made a 3D animation of Bala. I made a 3D version of Bala here, a little 3D avatar of him. And using Blender, I programmed some short animations. So here's the first one, which just used this. All I needed was this parameterization of the rotation that I just gave in quaternions. So here's a few stills of the animation that I made. So here's Bala when theta is equal to 0. Here's Bala when theta is equal to 6, pi over 6 rather. Now theta is equal to 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, and so on, all the way up to 12 pi over 6, or 2 pi. So as you can see, this performs as theta ranges from 0 to 2 pi, we get a full 360-degree or a rotation loop about the x-axis. So in a similar way, we can animate rotations about the y-axis and the z-axis. And of course, I just used large theta steps so I can go through the slides quickly, but you can use smaller theta increments and create a much smoother animation. So a 360-degree rotation about the y-axis is given by this parameterization. The only difference is that now my axis is given by 0, 1, 0. And the 360-degree rotation loop about the z-axis is given by a very similar formula. Now my axis is given by 0, 0, 1. There's no I or j terms. So we can actually see the Blender versions of these animations now. So earlier we saw that there's two ways to track an orbiting object. Remember that we had a situation where Bala was here, there was a particle orbiting around Bala, and there was two ways to track it. There was a non-trivial loop, and there was a trivial loop, both of which tracked this orbiting particle, our orbiting object. So we just parameterized the non-trivial loop using quaternions. But what about the trivial loop? I can also do the trivial loop in my head. It's just this loop. Can we parameterize the trivial tracking loop? So as a hint, remember how we decomposed the trivial loop into non-trivial rotation loops. In particular, we had this decomposition of the trivial loop into two non-trivial rotation loops. So see if you can use this decomposition to write down a parameterization of the trivial tracking loop.